Dear friends, this is a recap of lecture 7. So I'm just recapping it. It is not new lecture. Actually, there are some new parts. You can, if you follow this lecture, you can get some new ideas. So let's see. So equation of motion for undamped system is excited with some force F naught sine omega t or F naught cos omega t, or it can be F naught e omega t. So this is a spring mass system without considering the damper. So the forcing frequency, the forcing part represented F of t is equal to F naught sine omega t. Okay, so the equation of motion becomes x naught dot dot x dot plus k over mx, which is equal to F naught sine omega naught t plus over m. So this k over m is omega n squared. So x dot dot plus omega n squared x is equal to F naught sine omega naught t over m. So this omega naught is the forcing frequency and omega n is the natural frequency. So particular solution for this case is f of t, f naught sine omega t. Okay, because here f of t is equal to f naught sine omega t. So the homogeneous part of equation is this one, and the solution for the homogeneous part is x homogeneous of t is equals to a sine omega n t plus pi. So here we have a and the pi. We have to determine, or we can represent it in terms of a sine omega n t plus b cos omega n t. Now one can use that. And the particular solution x particular is equals to x sine omega t. X is the amplitude. Okay, and this is determined from the similar equations. Okay, for when we apply this equation into the main equation, then we can get x. And this equation, this a and the pi are obtained from the initial conditions of x naught of t and x dot naught of t. Okay, so we differentiate equation g twice to obtain x dot dot of t. Hence, the acceleration can be obtained from the solution equation. So x minus x omega naught square sine omega naught t is. So let's substitute h and this g into the main equation. Okay, in the equation. Then finally we can obtain the x, the particular solution for constant x, or the constant amplitude x is obtained by substituting x dot dot p and x of p. Okay, that gives us this equation. Okay, this is either we can represent it in terms of delta s. Okay, so x particular t is equal to delta s t over 1 minus omega naught over omega sine omega naught t. Okay, therefore the general solution is obtained by adding up or superimposing particular solution with complementary solution or homogeneous solution. So this is the particular solution and this is the homogeneous solution. And how we can find a and pi, they are from substituting these initial conditions. So by that, we can find a is equals to x naught square plus b naught over omega n square. and pi is tan inverse of omega naught omega x naught omega n over v naught. This v naught means x distinct x naught dot, and the general solution becomes this. This is the general solution. Okay, so the general solution is obtained by superimposing complementary solution, that is for the with natural frequency, and particular solution with forcing frequency. Okay, so this is the general solution. It is sinusoidal because we consider x homogeneous is equals to a sine omega nt. So this is complementary solution, a graph obtained from complementary solution, and this is a graph obtained for particular solution. And summing up to, we get the general solution. So this is a general solution. Okay? X general is equal to x complementary plus x particular. Okay? So the complementary solution of the equation of motion represents the natural response of the system and oscillates at angular natural frequency. This is the transient response. Okay, this is the transient response. The next, the particular solution of the equation of the motion represents the forced response of the system, and it oscillates at the angular frequency, angular forced frequency. This represents the steady state response. Okay, this is steady state response, and this is transient response. So the general solution of equation represents the combined response of the system and the sum of the complementary or natural and the particular or forced response. So this is the sum of two responses. So the above figure shows two responses at different frequencies. Recall that the values of omega n comes from the physical characteristics of the system, like mq, and omega naught comes from the forcing being applied to the system. These responses are summed and to achieve the blue color. This is the blue color one is the general one. Okay. Blue color shows us the general response because we summed up the particular one and the complementary together. Then the superimposed part will give us this type of solution. Okay. Steady state response. So in the reality, these superimposed responses do not last long. Every real system has some damping, and the natural response of the system will damp out. As long as the external harmonic force is applied, or the response to it will remain. When evaluating the response of the system to a harmonic steady state response, when the natural response has been damped out and the response to the forcing function remains. So amplitude of the force vibration. So as we have discussed, magnification factor x over delta static, which implies 1 over 1 minus omega naught over omega n squared. So this graph represents three different regions of the relation between magnification factor and frequency ratios. Okay. This is what we have discussed previous. Now let's see what rotating unbalance. One common cause of harmonic force vibration in mechanical systems is rotating unbalance. Okay. So this occurs when the axis of rotation does not pass through the center of mass. In this situation, instead of the center of mass remaining stationary, it experiences some acceleration. This causes a force on the axle that changes direction as the center of mass rotation. We can represent this as a small mass element rotating about the axis of rotation have some distance called an eccentricity. So the distance between a rotating mass. For this, we can see some diagram. Let's see. Look, this is the rotating mass. So this is a small mass considered. Okay, the distance from center of rotation to this mass center considered E, which is called eccentricity. Okay. So the forced angular frequency omega naught in this case is the angular frequency of the rotating system. Okay, this is what we call. Now let's see forced damped oscillation. Still, we have seen only undamped system, but if damping is also considered, what will be the questions? So let's drive our damped spring object system by sinusoidal force. Suppose that the x component of this, the driving force is given by f of t is equal to f naught cos omega t, where f naught is called the amplitude or maximum value, and omega is the driving angular frequency. The force vary between f naught and minus f naught. Means there is a change of f naught. The cosine function varies between 1 and minus 1. As we know, if it is cosine 0, then it is positive 1. If it is cosine 180, then it is minus 1. So the cosine function lies in between 1 and the minus 1. So define x of t to be the position of the object with respect to equilibrium position. The x component of the force acting on the object is now the sum of f of t, which is equal to f naught cos omega t. Actually, for this, I have to refer this figure. Okay, consider this. Let me resolve this force. So this force have two components because there is centrifugal force here acting, and that centrifugal force will be resolved into x and y. Okay, this is the force Fc. Yeah, it is all about this thing. So the component of the force acting on the object is now the sum of f of t, f naught cos omega t minus kx minus cx. Why? Because we have both damping system and the stiffness. Here we have damper. Here we have stiffness. Okay. Okay, f naught cos omega t minus kx minus cx, which mx dot dot. That is. So this finally gives us mx dot dot plus cx dot plus kx is equal to f naught cos omega t. This is a general form of equation. Now let's assume the solution is to be given as a function x of t is equal to x cos omega t plus pi, where the amplitude x is a function of the driving angular frequency. So here what we are, this is the particular solution actually, what we are talking. So x particular, let's use the frequency domain. This is a frequency domain. Okay, most of the time what we have learned is x of t, that is time domain. Okay, x of t is time domain, and f of omega is omega domain. So even here we can represent it in terms of omega. Anyways, so x of omega using frequency domain, we have f naught over m over radical of Cn square omega square plus omega naught square minus omega n the whole square. Omega n naught is the forcing frequency, and this is natural frequency. So the phase constant pi is also a function of driving angular frequency, omega. Okay, it is omega naught, not only omega. So pi of omega, which is equal to tan inverse of C over m times omega over omega naught minus omega n squared. And the natural angular frequency associated with the undriven undamped oscillation is k over m, radical of square root of k over 1. Okay. Now let's see the condition here. In this equation, we have this omega naught minus omega n. So C over n also there. If we take out omega, here I used different type of representation that is kind of confusing. Okay, so this should be omega n. Okay, this should be omega naught. Yeah. So x naught of omega versus omega graph is here. So when C over m too much less than 2 times omega naught, we say the oscillatory is slightly damped. For lightly damped driven oscillator, after transient transitory period, the position of the object will oscillate with the same angular frequency as the driving force. That means it is coming to this point. Okay, this is the situation. This is the point where resonance will happen. Amplitude x naught of omega becomes too much high here, and that is the point where a resonance occurs. So the plot of amplitude x of omega versus driving angular frequency for the lightly damped force oscillator is shown here. So if the angular frequency is increased from 0, the amplitude of x, which is equal to x of omega, will increase until reaching maximum when the angular frequency of the driving force is the same as the natural frequency omega naught. This is called resonance. So when the driving angular frequency increased above the natural angular frequency, the amplitude of the position oscillation will decay or diminish. So how we can see those things? Dx over dt is equal to 0. To find the maximum by setting the derivative of equation to 0, we can find those vanishing points. Dx over dt is equal to 0. Okay, so from this, what we can get, omega naught is equal to c over n square over 2, which is equal to omega n square. This implies omega n is equals to omega naught square minus c over n square over 2. For the lightly damped oscillating, omega naught too much greater than half c over m. So the maximum values of the amplitude occur when the natural frequency approaches excitation frequency. So this is the point where the resonance happens. And the amplitude at resonance is then lightly, amplitude at resonance will be x resonance is equal to x of omega n is equal to omega naught, which implies f naught over c omega naught. Okay, so this is the condition of resonance. For damped, sinusoidally forced and damped oscillation type. Okay, So let's see some problems. What type of problems are related to the previous discussion? Let's synchronize it. For example, we have some system which is fixed on some cantilever. Okay, so let me read it. 10 kilogram fan is, we have fan here, fixed at a lightweight beam. This is a beam. And this is fan. And the weight of fan is 10 kg. The static weight of fan deflection deflects the beam by 20 millimeters. Delta SCT is given. Delta SCT, which is equals to 20 millimeters. If the blade is designed to spin at the rotational speed of blade omega is equal to 15 rad per second, and the blade is mounted off center, which is equivalent to 1.5 kg. Okay, the centric mass is considered 1.5 kg at 50 millimeters from the axis of rotation. So centricity is equal to 50 millimeters. Determine the steady state amplitude of vibration. So now we are requested to find x. Okay, what is the value of x? So that is the question. Another question, second question is, you are designing a stylish fan that uses only one blade. So this is a kind of different design concept using a single blade for fan. And approximate that the blade has a narrow plate with density per unit length of 20 grams per centimeter. Okay, specific density is given 20 grams per centimeter. And the base weight of the rest of the device, except for the blade, is 4 kg. Okay, and the whole thing is mounted on a lightweight beam. Here also lightweight beam is there. Beam, a single blade fan. Okay, this is 3-blade fan. Okay. Beam case. If the spring constant of the beam is K is equal to 1000 Newton per meter, find the length of the blade then will cause the resonance. If the fan is designed to spin, so the rotational speed of fan also given. Now what we are going to find is find the blade lengths that can cause resonance in the system. Okay, this is the question. Question number 3. Here we have also another system. A 2 kg box of orange juice contains the instrumentation shake oil. Okay, an engineering student decides to get smart and connect the juice box with the spring. Okay, here, which has a spring constant K is equal to 25 Newton per meter, and applies a periodic force. Okay, so this is kind of force which is F is equal to 5 sine 5t. What is the maximum amplitude of the periodic motion and magnification factor at a steady state? So question number 3 related with this schematic diagram. And question number 4. The world's smartest fairies wheeled mass is equal to 20 kg is mounted on the end of horizontal beam. Okay, here we have the horizontal beam, and we have a ferry of 20 kg is here. Okay, for non-apparent origin. The wheel is mounted centrically in such a way that the centricity is equivalent to a mass of 5 kg located 0.15 meter. So centricity 0.15 meter, and the centric mass is 5 kg away from the axis of rotation. Okay, the static weight of the ferries will cause a deflection of static deflection delta ST is given, okay, in the beam. Given that the wheel spins at rate of 15 rad per second, find the steady state amplitude of the vibration. So this is also another case. The last question here is the fifth question. 150 kg mass is supported on the 3 springs. We have 3 springs here, equivalent KKK having stiffness. Okay. Find the spring constant K required for a magnification factor of 2. So the magnification factor 2 is given, and the forcing function f of t is equal to 25 sine 40 is given. So it is spring mass system with excitation force f of t. So these are questions to be solved. So maybe in the next time, I will solve these questions one by one. And if someone helps me by solving these questions, please attach your Word file or kind of whatever your work. Please attach for these 4 questions and check your answer when I give you the answer. Okay, so this is all about. And I'll give you again another practical question. The electric motor and its base have a combined mass of M32 kg. Okay, the overall mass of the electric motor and everything is given M, which is 32 kg. Inside the motor, there is an unbalanced rotor which can be modeled as seen at right. Okay, here we have a small mass at eccentricity E. Okay, the base of the motor is constrained to move vertically. Okay, the base is here. Base is constrained. Okay, this is the foundation of the base. The motor is running at a constant speed of omega 9 rad per second. This omega 9 rad per second. Each of the 4 springs, so there are 4 springs, spring 1, spring 2 behind, spring 3, 4. So we can model them 2K, 2K because there are 4. 4 springs has constant stiffness K is equal to 188 Newton per meter. The mass of imbalance, including in the 32 kg total mass, is 0.8 kg. So this eccentric mass is 0.8 kg. What is sensitivity of the imbalanced mass E would result in a steady state amplitude of the system of X is equal to 10 millimeter. For the purpose of this problem, please ignore the damping. C is equal to just ignore damping case. Just take this as 0 and please solve and attach your answer to my site, or you can give it to me on my email address. Okay, or you can simply attach it. Okay, this is my email address. Someone can send it. someone can attach samayat@f@iitk.ac.in. So this is all about today. Thank you very much for your attention.